Hey guys, Chili here coming back at you with another installment of the Red Pill series. Today we're going to be talking about the heap, and that is going to bring us into the deeper topic of memory paging and virtual memory, virtual address translation, stuff like that. A lot of deep concepts here. I'm going to be going over the fundamentals, the theory that'll enable you to understand specific implementations. Back when I covered things about pointers and stuff, I talked about the stack, and I went into some detail about how the stack works. But I never really went into details about how heap allocation works, and that's because it is pretty damn complicated. But we're going to go into it a little bit here today. So if you remember from my video on the heap, this is the kind of fictitious memory space that I've shown you. It's similar. It has many similarities with actual memory maps like for Windows or for Linux. But it's just one I made up to demonstrate the fundamentals that I was trying to teach you, the concepts. Now, here, there are some things you might notice. Some things like, you might think, am I in the matrix? A little glitch in the matrix here. First of all, where are all the other programs in this memory space? I mean, obviously, if we're running our program on operating system, usually there's going to be a lot of other processes sharing the memory with us. But this memory map only shows the usage by our application. Where are all the other processes? And the fact is, here's the deal with processes in user mode. They're all in their own individual universes, their own individual sandboxes, and they're not aware of each other. Each user mode program feels like it is in its own universe created just for it. Now, in reality, the situation looks something more like this. So basically, all of the memory addresses are all divided up into pages of a certain size. Let's say 4 kilobytes, doesn't really matter what the size is. So memory is all divided up into a big array of pages. Now, the memory addresses that any process sees, that is virtual memory. But that is not the actual addresses in the physical memory. So if the process writes to address 20, that is not going into address 20 in the RAM, that is going somewhere else. So the way it works is the operating system maintains basically a table for every process, and that table is used to translate between pages in that process's virtual memory and pages in the actual physical memory. And when a process tries to access data at a certain address, every access has to be translated from the virtual address into the physical address. Now, in general, any given process isn't going to be using up the entirety of its virtual memory space. Lots of that is just unused. And in your tables here, that is represented by many of these pages not having a mapping into physical memory. And if a process tries to access pages in its virtual memory space that aren't mapped, that is going to cause an exception. That's going to cause, a page fault or whatever. And that you get that when you mess up with pointers and you're pointing to some memory that you don't actually have access to because it hasn't been mapped into your process memory. Now, you might think this is actually a huge pain in the ass. Why do we do this? I mean, the operating system has to maintain all of these tables of mappings. Every time the process accesses some memory, it's got to translate that virtual memory address into a physical address. That's a hell of a lot of work. Where's the benefit? Well, there's tons of benefits of this. One of the main benefit, I would say, is that every process is in its own sandbox. So, for example, if all the processes were just in physical memory, one process could mess up its pointer and write to memory of another process and trash that process. Or it could write to memory of the operating system and take down the whole system. But because we have this virtual memory, if a process accesses, memory in a bad address, it's just going to cause a fault, and maybe that process will get trashed, but it can't trash anybody else's work. Everyone is in their own sandbox. Very nice. Another advantage is, let's say a process needs to allocate a very large block of contiguous memory. It has to be all contiguous addresses in its virtual space. Well, if a block of memory doesn't exist in that size in the physical memory, you wouldn't normally be able to do that without the virtual memory system. But with virtual memory, you don't have to have a huge contiguous block in physical memory. You can just allocate this page to here, this page, or we don't have any pages left. This diagram doesn't have enough pages, but you can allocate pages from all over the place into consecutive spots in the virtual memory, and now you've got a big contiguous memory. Your program feels like it has a big contiguous memory space, although in reality, it's all over the place. Another advantage of paging is it allows you to extend the physical memory of your system. So you can give your system a memory space of 1 gigabyte, even though maybe you only have 32 megabytes of RAM. And the way you do that is all of those extra pages that don't fit into RAM, you put them on the disk in a paging file. And what happens is when a program wants to access one of those pages that aren't in RAM, it is going to evict an existing page in RAM to the disk, and then is going to load the disk paged page into RAM. So it swaps out pages as they are required by applications, and that allows you to extend the memory space. Of course, the swapping is slow, but it's much better than just your computer crashing because it's out of memory. So yeah, there are tons of benefits of this paging system, but the obvious downside is, again, like I said, more complexity of having to manage these tables. But the biggest downside is the speed impact, right? Because now when the CPU wants to access some memory in your application, it can't just load from that address. It's got to translate every memory access from a virtual address into a physical address before it can load or store. And that can be very slow because you've got to walk through this table of information, this map, and try to figure out what virtual address maps to what address in the physical memory space. Now, the CPU gives us some hardware support to make this very fast, and that thing is called a translation look-aside buffer. And what that does is it just maintains a cache in hardware of basically translations between virtual addresses and physical addresses. So if an address is in a place where you often look, it's going to be incredibly fast to do a lookup or the translation from virtual to physical. But if it's in something that you haven't looked up in a while, it's not going to be in the cache, so you're going to have to do a translation, which is going to take a while. But yeah, that's the basic idea of virtual memory. When the operating system loads a program, when it creates a new process, it is going to allocate some pages for it, for the code and for the stack. And when your program allocates dynamic memory on the heap, that is going to cause additional pages to be allocated to your process and mapped into your process's virtual memory space. Now, sometimes processes can share the same physical address space. For example, if you've got a DLL, you've got some kind of library code like Windows DLLs, user32. That code is going to be shared by many programs on the system. So instead of copying that into different physical memory addresses for each process, it shares the memory. So the space in one process can be mapped to the same physical memory location as a page in a different process. And here they're sharing the memory. And these tables, they contain information like for each page, what kind of access does that process have? Can it read to the memory, or can it read and write? And, a bunch of other things. But we're not going to go into those kind of details, just the basics for now. So now that we have an idea about the virtual memory that your application sees and the actual physical memory, and the relationship between them, let's take a look at what happens when you allocate memory. So in C++, you're going to use the new operator to allocate memory. And the new operator is going to do two things, right? It is going to get some memory, get a block of memory, and it is going to call the constructor for the thing that you are newing. Now, to get the block of memory, what one implementation might do is it might call a function called malloc. So new is C++. Malloc is how you allocate heap memory in C. So malloc does not construct, obviously, because there's no idea of constructors in C. All it does is it secures a block of memory on the heap. So you pass it a number of bytes, and it will return you a pointer to a place in memory where you can use that many bytes. They are yours. And then malloc may or may not call a function from the OS to do some virtual allocation, and that will allocate pages of memory that the OS will map into your memory space. Now, the idea of malloc, the memory allocation, it could do many different things. It depends on the implementation, of course. There's many different strategies. But in general, let's say you want to allocate, let's say you want an int, okay? So that means you're going to need 4 bytes. So let's say the C++ new implementation calls malloc and requests 4 bytes. Now, if you don't currently have anything on the heap, it's not going to have any pages to put that memory in. So malloc is then going to call the OS function to virtually allocate a page. Now, pages, you can't say, give me 4 bytes. It doesn't work like that. Pages have a fixed size, and you have to allocate a number of pages. So if your page size is 4 kilobytes, you are going to get, at the minimum, 4 kilobytes. So now the heap requests 4 kilobytes. It's got this memory. So it's got 4 kilobytes here, but you only need 4 bytes, right? So what does the heap do? Does it just put your 4 bytes in here and waste the rest of that? No. It uses the rest of that memory for subsequent allocations. So in order to do that, it has to keep track of, what parts of this memory space are used and what parts are not used. And it does this in a couple of ways. The first thing it does is, obviously there are different implementations, so I'm only going to give you one example. But a very simple example of a heap is you've got this memory space, that's your heap, consists of a number of pages that you've allocated into your memory space. You've got objects, and then you've got, spaces between them. Maybe you had an object in here, but you deleted it, so now it's empty space. Or maybe this space was left open for alignment reasons, doesn't matter. So what you have is you're going to have a data structure of linked lists, and they're going to give you linked lists of start addresses and sizes. So and you call that the free list. So it's going to give you, you've got a free block here, and then the next element in the linked list, you've got a free block here, etc., etc. So the heap is going to maintain a table, some kind of data structure that's telling you what spaces are empty. Another thing that the heap is going to maintain is for every object in the heap, at the beginning of the object space, it's going to maintain a little bit of data to remember the size of the object and maybe some other things. And we'll look into that in a second. Because remember, when you call delete, you don't pass it a size or anything, you just pass it the address, but it knows how to delete the whole object. And the way it knows is it stores a little bit of information at the beginning of the object on the heap to tell you how big that allocation was. So malloc has a lot of responsibilities because, it has to, first it has to be able to allocate new pages, virtual pages, into the memory space of the process by calling the OS function when they're required. It needs to be able to keep track of all of the available space in the currently allocated memory. And when you call malloc, it is going to have to be able to find empty spaces that are big enough to hold the requested allocation. And again, C++ gives us delete, and delete is going to call the destructor and then free the memory, and it might call the C function free, which will free that memory. And free is going to update the free list, right? Like if you delete object 1 here, now the free list, this node will be deleted, and this will all be one big free block, and it will then point to this second block here. That would be one way of updating the free list when you call free. One little side note here, when you call free, it doesn't immediately return memory to the OS, because think about it, if you've got a page of memory and you've got some allocations on there, just because you freed one doesn't mean that page is ready to be returned to the OS. There might be other allocations on that page, and even if you free all of the allocations on a page, That doesn't mean that it's going to be returned to the OS immediately for a number of reasons, but often the allocation strategy of the allocator in the C runtime holds on to pages because you might need to allocate them again anyways. So it likes to keep hold of pages once they've been allocated. But I believe if you free enough memory in enough contiguous pages, then it might start to return that memory to the OS. But there's a lot of variables, and it is very implementation dependent, obviously. But yeah, that's the basic idea of how the heap works and virtual memory and paging. Note, and this is something super dumb, but the heap, as we call it, the free store, has nothing to do with the computer science data structure of a heap. It's not a heap at all. It probably there's many different ways of implementing a heap, but the simplest is, just a linked list plus some data at the beginning of every allocated object. So yeah, it has nothing to do with the computer science heap. I don't know why they named it that, but whoever came out with that decision should be punched in the face. Doesn't make any sense. Now let's take a look at just a couple of practical things with code that we can do with this concept. So here in this code, I'm doing some memory allocations. I'm setting some values. I'm not freeing my memory. I'm a bad boy. Spank me, daddy. Let's see what happens when we run this. And we step through it in the debugger here. So my capture software is totally fucking with me. So yeah, there we go. So we'll step over this. We'll allocate the pointers. We'll write some into memory, some data into that memory, and let's take a look at this stuff here. So let's look at pstruct. So here's the address of it. We can see here's the 42 that was written into A, and here's we didn't write anything into B. Here's the 42 that was written into C. So this is the memory allocated on the heap for our struct. Now, interesting, if we look up beyond this memory a little bit, we see some interesting things here. This memory here is that memory I was talking about that goes before the allocation block. This here, this address, this 0C, that's 12, that is actually the size of the allocation, 12 bytes. So we've got three ints here. One is the size of the allocation. This 48, I have no idea. This 1, I have no idea what that is talking about. Some of these might be references into the data structure that it uses for the free list or something else. I don't know. If anyone knows, let me know in the comments. But I'm not going to bother to figure it out. But yeah, it's neat that you can see here, this is the data. This is where it looks to see how big this block is in the allocation. We can verify that if we look at the P array. Now here's the 22 that we wrote at the beginning of the array. Here's the 22 that we wrote at the end of the array. And if we look up again, we've got blank space, and then we've got three ints. And here, this 45 hexadecimal is 69 decimal. So this is the size of the array that we allocated right there in memory. And if we look at our heap as a whole, we can see that all of our objects are basically allocated together here. Let's see if I can find them. Here is the structure. Here is the int. We can see here it's allocation block size 4 bytes. And here is the array. You can see the allocation size here is 69 bytes. Now, normally for the programs that you write, using the C allocator is good enough for our purposes. Or sometimes if you want to do custom allocation, what you do is you allocate, you use the C runtime to allocate a big block of memory, and then you do custom allocations inside of that memory space. You write custom allocators for things like your containers. But if you wanted to write a custom allocator or wanted to allocate a big block of memory or whatever, you could skip the C runtime altogether and allocate directly with the operating system memory allocation functions. So let's try that out just for shits and giggles. So here's a list of virtual memory allocation functions for Windows. You can see there's a bunch of them in here. The one that we're probably interested in is virtual alloc, or virtual alloc. EX is extended one, but I guess we could just try the basic one to start off with here. So we give it an address in our virtual memory space that we want to allocate into, and we give a size, number of bytes that we want. I believe it's a number of bytes. And then there's allocation type and protection. So let's see here. Now, I believe this address here has to be a multiple of the allocation granularity, the granularity of memory allocations. And you can determine the size of a page and the allocation granularity on the system with this function here, get system info. And I guess the size here also has to be a multiple of the allocation granularity, or maybe a multiple of the size of a page and no less than the granularity. I have no idea. We're just fucking around with shit here. Let's go to get system info, and let's first get some information about our system here. So this is going to fill a system info structure with some information. Let's look at system info structure. No, don't. Fuck. All right, well, this is what this is. Let's go back and let's open this in a new window, new tab. So we want to call get system info long pointer to system info. So we want a system info structure. We'll put one of those on the stack, and then we'll just call it info, and then we're going to call get system info. There we go. Pass in an address to our structure, and then let's see if our IntelliSense will save us here from reading. So info dot page size. So here's our page size, and let's go std cout info dot allocation granularity. That's probably the other one that we want to know about. And we'll just do std cin.get. All right. So if we run this, we should get some infos. So page size is 4 kilobytes, like I told you. The granularity is basically 64K. So that means that we should, I guess, maybe use addresses and sizes that are a multiple of 64K. I'm not 100% sure, but that's what we're going to do. So let's go back to the page here, and we're going to call virtual alloc. So this is in option. These are all ins, and it returns the pointer. So very rare for a Windows API. It actually uses the return value to return something to us, and it's a void pointer. So let's go, we'll go auto, P is equal to, and we'll go reinterpret cast car pointer, virtual alloc. All right, so we need to tell it, here's the thing. We need to give it an address to allocate into, but we don't actually know which addresses are going to be available. And I'm sure there is a very good way of finding out which ones are going to be available. I am just going to pick a random address and see if it works, because that sounds like fun. So let's start. Let's go 500. All right, now the last 4 zeros, these have got to be these guys have got to be empty, right? Because it's got to be a multiple of 64K. So let's try to get an address at 5690000. And we've got to reinterpret this to a long pointer void. So we go reinterpret cast void pointer. We can reinterpret an int to a pointer. Normally not something you want to do. Size, is this in bytes, or is this in pages, or is it in granularities? I don't know. Size of the region in bytes. Okay. Round it up to the next page boundary. Include all pages. So apparently we can do it in the pages. Granularity maybe doesn't mean anything, maybe means lots of things. To start off with, let's just allocate that's a size of one granularity. So 1000. And what else do we want? Allocation type. So I think the normal one is commit. So let's just take that. There's a whole bunch of options you can OR together here to make things happen, all sorts of things you can do. But I think commit is really all that we need here. Now, for the memory protection, we want to be able to read write. So let us look into this. Page execute. We don't need page execute, but we need read and write. So let's go page execute, read write copy, no access, read only, read write. Here's what we want. We want read write. So put the read write into there. And I believe that is all. Yeah, we gotta reinterpret cast, gotta close that parentheses there. So this should be good, except of course that we don't know that this address is going to be available for us to map into. But we can try. And then let's just go, star p is equal to, 69. And std cout star p. We're going to convert that to int so it doesn't just output some weird ASCII character. Let's build it. See if it builds. Does build. Let's run it. Exception thrown, right access violation. P was null pointer. Okay, so obviously our virtual alloc failed and it returned a null pointer. So I imagine the reason why it failed is because this address is no good. Let's just try a couple of other ones. All right, so after plumbing around and choosing different addresses, I found one that seems to work and probably won't work every time because the program loads things into different places in virtual memory, or Windows loads programs into different places in virtual memory every time to prevent bullshit. Okay, this time it didn't work, so that's fine. Break, stop, run again. This time it did work. And see here, we got 69. So we wrote to the memory, we read from the memory. There you go. So we've allocated a virtual page into our memory space directly from the operating system. Now, obviously, this strategy isn't very good because you can never know what addresses are going to be available in your virtual memory space at the compile time. Now, the easy way to do this would probably be just to pass in null for the address, and that would just tell the system to choose the address for you. So if we did that, let's see here, virtual alloc. So we must make this guy null pointer. And what do we do? Let's output the actual address that it gives us then. Std cout p std and l. So if we run this, now it should never fail because it just gives us an address. And why are you not outputting anything for this? Oh yeah, so the overload for cout for car pointer is it interprets it as a string, not as a pointer. And yeah, okay. So we can just cast this. And I'll do it the right way because it's a pointer cast. I will reinterpret cast to void pointer. And now it will treat it like a motherfucking pointer and it will give me the address. There we go. So the address is, and it gives us in hex, is 3000. That's the address it gave us when we did the virtual alloc. All right, that's cool. Now, what if we don't want what if we want the control, but we also don't want to play Russian roulette? Well, what we can do a bunch of things. We could go into std. Let's go to std cout info dot minimum application address. It's std and l. So we can show the minimum and maximum, or we can get the minimum and maximum addresses, the address space available to us to allocate in pages in from this info structure. So that's minimum. We also want maximum, I believe. And I want to see these in hex, so I guess I do std hex, please. I hope so. I hope that's the one I want. And we'll do that here as well. Show me that shit in hex, please. I hope that doesn't affect all of the numbers. It affects all the numbers, doesn't it? Yeah, it affected all the numbers, didn't it? Yeah, well, whatever. Okay, so yeah, so we can get all the memory from here to here. Yeah. Oh yeah, because I'm running in x86 mode. What if I put her in x64 mode? What do you think you'll see then? Now we have a bigger range of addresses you can allocate in this range here. Much more memory. And what it gave us was 000D. It gave us the D. Now, if we want to choose our own address, if we want to choose our own adventure, what we can do... All right, so I set up a basic loop here, and it's going to ask the user for an address. It's going to input that as a hex number, and it's just going to report that back onto the command line as a decimal number. So for example, if I ask for the address, 140, you're going to get 65,536. That makes sense, right? Now, what we want to do is we want to validate in this loop. We want to be validating that address to make sure it's okay before we try to virtual allocate. So what we have, if we want to do things the hard way, is we can do function virtual query, and we pass it a pointer to a buffer of memory information, and it'll give us information. We can query into any address, and it'll give us information, I believe, about the pointer to the base address of the region of pages to be queried. Now, I don't know where it gets the region of pages. I don't know how you determine the size of the region, but it's not that important, is it? All we want to really know is if a page at a certain address is available for us to map it into our memory space. So, retrieve information about the range of pages and the address. Yeah, okay. So, we need to create a pmemory basic information. We'll put it, I guess, here. And we will, no. That's just a... That's a struct, not a pointer, right? Fucking hate all those goddamn Windows type defs. B info, I don't know. That's right. What is it? Yeah, what is this? Type def. Oh, it's a pointer. So is this memory basic information then? Yeah? Okay, good. Thank you. Why do you gotta read type def all of the structs as pointers as well? Are you afraid of typing a star? It makes me so mad. Anyways, so now we want to call virtual query. What's the size return actually? What is number of bytes returned in the information buffer? Okay, yeah. So we pass it a pointer to the buffer. We pass it the size of the buffer. This one will return the actual size in the buffer. I don't know when or where that would be interesting, but we're going to ignore that. So query for... What was that again? I don't remember. Virtual query. Got it backwards. Okay. So we're going to virtual query. And we're going to pass it the address that we want to look at, which is just going to be reinterpret cast void pointer adder. And we're going to pass it a pointer to the buffer of info. And we're going to pass it the size of the b info. And we're going to ignore the return value. And then we're going to look into this buffer. binfo dot state maybe, or type. I'm believing size. Okay, there's where we get the region of the size for whatever reason, protection, I don't know. We want the state. We want to see the state. Is it allocated or not? Now the problem with this is that we don't know what this is. D word. It's just a D word. So not much information. Thank you, C. But if we go into basic memory information and we look into type, private, there we go. No, not type. Protect, no, state. Commit, free, reserve. So we want ones that are free. So we do finished is equal to binfo state and We'll do a bool be info state and mem free. So I don't know if state can be a mask of multiple flags, but just to be sure, we're going to do it like this. So then if not finished, you will never get this. You will never get this. So we keep looping until we get one, and then we can allocate it and use it. Let's see if this works. I don't know. This is the first time I've ever done this, so I'm not optimistic. But let's ask for address 1000 because I'm pretty sure we will never get that one. You will never get this. Okay, let's ask for address 30000. And there you go. We got it. Beautiful. Wait. 19660. Wait, that's the address. 000000 is... Fuck. P was null pointer. So we tried to allocate it. Let's just try to break. Let's see here. Stop. Stop it. Finish is equal to that. You will never get this. And we get a new address. Output that address. And finish is true, so query was successful, but the allocation was not successful. That's the part that I don't understand. Why is the query successful? Why is it free, but we cannot allocate it? All right, so the last error in the debugger tells us that the last Windows error was error invalid address. Now I got an idea. I got something I want to try here. So what if we go into here? We're going to debug. We're going to step into what address would you like? We'll step over that, and we'll step over this, and this will pop up. And let's ask for address 30000. All right. It is going, and you can't see this, but it is going to output that as a decimal number. Then we're going to do the virtual query. So the last error was success. After we do the query, it's success. All right, so I figured out the problem. Chili has saved the day, and the reason is some kind of bullshit. So when you commit memory so you can start to use it, you have to first reserve it. So you can reserve memory at some point and then commit it later on, or you can commit and reserve altogether, but you cannot commit without reserving. Now the thing you might be asking, and the thing I asked myself, was, well then why the fuck did it work when I only had commit? And the reason for that seems to be some kind of compatibility hack. So a lot of applications forget to set the reserve flag when they mem commit, and the memory management lets it slide if they also pass LP address equal to null, which is what we were doing before when it was succeeding. So I had been mistakenly led to believe that it was okay to just pass in commit, when actually you have to do commit and reserve. There's only like basically a dumb kind of permissiveness built into virtual lock. So what I can do now is, if I run this, I can say, give me address 1000, and that doesn't work. Give me address 30000. Now, of course, because we're using C in here, get isn't going to work down here. It's going to pass right through. So I'm going to use KB hit instead. And if we run that, give an address, let's go for 3000 or whatever that number is. And it works. There you go. So we have now been able to choose our address and verify that it is available, and then allocate the page into our virtual memory using this Windows bullshit. Would you ever want to do this? Maybe, probably not, right? But it's something that you could do, and there are similar functions in Linux which allow you to do that sort of thing. But yeah, just a little fun bullshit playing around with Windows API stuff and memory management and all sorts of cool bullshit. But yeah, that's going to be it for today. Leave leave some comments if you have anything to add or you have any questions, or you can hit me up on the Discord for a more detailed. I don't usually answer really complicated questions over YouTube comments. It's not how I do. But anyways, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. I use that to basically gauge whether I should make more videos like this one, going into these nitty-gritty details or not. So yeah, click that like button if you want to see more like this, and I will see you soon with some more C++.